Hello, welcome to my video series of algorithms. This is part 2 of Module 1, the sorting algorithms. In this video, we will discuss insertion sort. We will focus on presenting the design and analysis of the algorithm. We expect that the audiences are familiar with the sorting problem and the selection sort algorithm. If not, you can review the previous video of this module. Recall selection sort. Its basic idea is to iteratively select the smallest element from the existing set of elements. To select the smallest element, the algorithm simply screens each element. In this case, it gives rise to its O(n)² time complexity, where n is the number of elements in the input set. The major limitation of the selection sort algorithm is that it cannot take advantage of easy instances. For example, even if the input contains a list of already sorted elements, the selection sort algorithm still needs O(n)² time. This is because it still has to check each element in the existing set to select the smallest element. In this case, our goal is to address such a limitation by developing a new algorithm that can run faster with easier instances. For example, if we are given a sorted list of elements, can the new algorithm run faster than O(n)²? Know that if an algorithm can take advantage for an easier input, it needs to recognize the pattern that corresponds to an easier input. For example, to take advantage of the fact that we have a sorted input list, we first need to recognize that the input list is sorted. In this case, verifying that the input is sorted becomes a simpler subproblem that needs to be solved by the more general sorting algorithm. Now, consider the simpler problem of verifying an input list is sorted. How much effort do we need for this purpose? We can perform the following simple procedure. We begin with the first element and compare it with the next one. If the current element is smaller than the next one, the two elements appear to be sorted. We then move on to the next element, and we repeat the process until all elements in the list are examined. This algorithm runs in O(n) time. Here, we can see the discrepancy between verifying a list is sorted and actually sorting a list. It implies that the algorithm we expect to develop should run in O(n) time with a sorted list as input. Now, if we generalize the verification process, we would be comparing the ith element and the i+1th element and repeating the process for all I. Note that we only compare the i+1th element with the ith element, but not the other former elements, because we have made a very important assumption. That is, the first I elements are sorted. We can expect that the assumption is true if we have repeated the verification process for each of the first I elements. Let's go back to the discussion of sorting. We know that in general, the input set may not be sorted. Therefore, when we perform the above verification process, we may find that the i+1th element is smaller than the ith element. Note that for the verification process to proceed to the i+1th element, it must have verified that the first I elements are sorted. Otherwise, it should have terminated earlier with an answer of no. At this point, if the purpose is to verify that the list is sorted, we can directly report no. However, if the purpose is to sort the list, we would have to take some actions to sort the first i+1 elements. Now, the problem becomes how to sort the first i+1 elements given that the first I elements are sorted. Like inserting a new poker card in a handful of already sorted poker cards, we simply insert the I plus 1th element to the proper position among the existing I elements. Consider the toy example of sorting numbers 1, 5, 3, 2, and 7. At the first iteration, we know that the first element 1 is sorted because there is only one element. At the second iteration, we compare the second element 5 with the first element 1. Since 5 is larger than 1, we can claim that 1 and 5 are sorted. At the third iteration, we compare the third element 3 with the second element 5. Since 3 is smaller than 5, we need to insert 3 into the proper position. To insert a new element, we iteratively compare it with its former elements until we find one that is smaller than the new element. For example, to insert 3, we compare 3 with 5. Knowing 3 is smaller than 5, we swap 3 and 5. We then compare 3 with the first element 1. Knowing 3 is larger than 1, we terminate the insertion. Similarly, for the fourth element 2, we know we also need to insert 2. We compare 2 with 5 and swap them. Then we compare 2 with 3 and swap them. Finally, we compare 2 with 1 and terminate the insertion. We repeat the process for each element and terminate when we reach the end. Here is a summary of the above idea as pseudocode. Note that line 7 allows the insertion to terminate earlier when the new element has been inserted to the proper position. If the input list is sorted, the insertion process will always terminate immediately, resulting in the anticipated O(n) time complexity. Now, let's move on to the analysis stage and first analyze the correctness of the algorithm. It is trivial to verify that if the first I elements are sorted, then inserting the I plus 1th element using the algorithm will sort the first I plus 1 elements. The algorithm begins with the base case of assuming the first element is sorted, which is obviously true. It moves on to consider the second element, and because the first element is sorted, the algorithm will sort the first two elements. It then considers the third element, and because the first two elements are sorted, the algorithm will sort the first three elements. You can see that the reasoning goes on and on until we reach the last element. In this case, we can see that the entire list is sorted. Such a reasoning process can be formalized as the proof technique called the mathematical induction, and we'll discuss it in more detail in Module 2. Then, we analyze the computational efficiency of the algorithm. We know that the pseudocode contains two layers of for loop. Both layers iterate through all n elements in the worst-case scenario. Therefore, the time complexity of the algorithm is O(n) squared. Recall that in line 7 of the pseudocode, we have incorporated a pretermination criterion, which reduces the time complexity to O(n) with the sorted list as input. Finally, let's look at the algorithm's space efficiency. Note that in the pseudocode, we only swap elements and do not copy any elements to new spaces. Therefore, it is easy to conclude that the algorithm only needs O(n) space to run. And it is further an in-place sorting algorithm that does not need additional space other than those holding the inputs. In summary, we have discussed the insertion sort algorithm in this video. In the next video, we will discuss the bubble sort algorithm. Thank you for watching and see you next time.